drop forging, flow forming, upsetting and extruding. Processing is applied to virtually all industrial metals such as steels, copper, brass, aluminum, as well as nickel and cobalt alloys. The common characteristic of all forging technologies comprises major cross-sectional changes, mostly reductions. This is a key distinction from other forming technologies such as sheet metal forming. The predominant forging process is drop forging. The die is generally a two-part female tool made of high-strength, heat-resistant steel, which is mounted on a strong machine. Subsequently, a red-hot rough forging is inserted. When the tool closes with enormous pressure, the hot metal will plasticize and flow into the cavity of the mold. Excess material from the rough forging flows into a residual slit between the die halves and forms a ridge, which will subsequently be removed. The reopening die releases a forging with the desired shape. The degree of deformation is limited by a number of factors. Forgings with complex or intricate shapes thus often require several forging steps using sequenced tool sets, each performing a limited portion of the total forming process. The final contour will only be achieved by the last process step. Open die forging resembles historic hammer forging, but nowadays the tools are much more powerful. Forging is performed by repeated press strokes with a tool fixed to the crosshead. Like the anvil, this tool will often be flat, but it can sometimes be semi-shaped to better accommodate the contour of the forging. Between the press strokes, the forging is constantly repositioned. This time-consuming procedure makes open die forging significantly more expensive than drop forging. For this reason, it is mainly applied if batch sizes are too small to justify the expenditure for the production of a die. Another important application field is for parts that are too big to be formed in a die, such as crankshafts for ship engines or shafts for power-generating turbines weighing more than 100 metric tons. The flow-forming process is characterized by a tool exerting such a high pressure on the rough forging that the material plasticizes and flows like dough. There are several variants of the process. In the case of teeth for dredger shovels, the hot metal is pressed into a steel die forming its outer contour, while a protruding core will shape its cavity. In other cases, the material is forced through a tight opening, shaping its contour, as for fancy shortbread biscuits. Furthermore, there are a number of additional variants. Shaping is often performed in several steps and may even involve different process types. This results in the production of sometimes very advanced components, such as intricately shaped hollow shafts for gearboxes. Flow forming is often performed using complex, highly automated plants featuring outstanding productivity. Machine and plant builders need seamless rolled rings made of high-strength materials for a broad range of applications, such as circular tracks for cranes, bearings and gear wheels, through to railroad and wheel tires. They are produced on sophisticated ring-rolling plants. Rough forgings are made from forged and subsequently pierced discs. Ring rolling requires advanced plant control systems, since the thickness, width, and diameter are interdependent. Steels are by far the most prevalent material group in the forging sector. They are inexpensive, easy to process, and can be alloyed and heat-treated to achieve the highest strength in combination with superior toughness. Moreover, steel parts can easily be recycled at the end of their life cycle. The high strength of steels often makes it easier to attain optimized solutions with respect to vital aspects such as weight reduction and enhanced efficiency. The alloy range is very broad, stretching from low-cost carbon steels up to high-alloy stainless steels. Second in rank among the materials processed by forging is aluminum, which is of particular interest for the automotive sector. Here, aluminum is used in undercarriages as well as for safety applications such as crash boxes. Furthermore, numerous other industry metals are forged. For example, the highly temperature-resistant metals nickel and cobalt are used in airplane jet engines. Airplanes also feature forged structural components made of titanium. Forged brass is used for synchronizing rings in gearboxes or for fittings. The list of metals processed by forging also includes copper, magnesium, and lead. Modern forging is a complex high-end technology whose products meet the highest requirements with respect to strength, reliability, efficiency, and value for money. In order to achieve these aims, the forger has to excel in a broad range of disciplines, such as material sciences, design engineering, process technology, production planning, and engineering, machining, and quality assurance. To this effect, he uses cutting-edge computer-assisted software tools. Of course, a particular focus is placed on the computer-assisted modeling and simulation of all phases of the forging process, from the direct input of 3D CAD design data from the customer to the definition of the necessary forming steps through to the design of the required tools. This includes the definition of vital processing criteria such as stress levels of tools and working parameters of the plant. This strategy makes it possible to detect any weak points in advance and to correct them by means of design changes, if necessary. The related software tools have, in the meantime, reached such a degree of maturity that it is now possible to design the operations of single plants on screen and to subsequently group them to complete production lines. Advanced features even include operations such as downstream machining or checking the size and frequency of quality assurance measures. Furthermore, computers can even perform the modeling of assembly operations as well as the integration of modules to complete systems. Using such tools results in highly efficient, cost-saving, and securely manageable production processes, yielding sturdy, reliable, high-tech products at the highest quality level. As a result of this in-depth engineering competence, the modern forger acts as a fully valued partner of his customer for the development of new products. His knowledge about the viabilities and limits of his processes is a crucial asset during the design phase of new products. While the designer of the customer will initially define a basic geometry as well as the corresponding set of requirements, the forger will contribute his knowledge about alloys and processes in